All right, thank you. Thank you, Director. So the plan is to have an informal chat about the composition lemma. The reason I wanted to do it is because I've received some requests for people who wanted a YouTube rundown of the lemma. And it's horrible to give a presentation to oneself because I know what's coming next. And it's much better if I get natural questions coming from the audience. So the questions are more important than anything I'm going to say. And also, if we don't finish, that's okay. We'll ask the director what to do about it. But before we run, I want to assess how much of a warm-up we need to do. So let me write the main statement. And then we decide how much review we need to basically get through the main statement. So here's the main statement. So we're given, so let me say, so Zn is defined to be the first n non-consecutive, the first n consecutive integers starting from 0. Okay, there's no algebraic structure. This is not Z mod n Z. Z mod n Z, it's not. And the statement is that for all f that go from Zn to Zn, and such that f has a unique fixed point which is attractive over Zn. So that means wherever you start in Zn, you eventually reach the fixed point. Then the maximum cardinality of the set over all permutation of, so this is sigma f sigma inverse of I, and here I want 2 minus I, take I in Cn. So this is the cardinality of a set. F2 is the composition of F with itself. This is always less or equal to the maximum cardinality over the symmetric group of here sigma F, sigma inverse of I minus I, absolute value, and Zn. So the statement being about composition, the statement is called the composition lemma. Okay, so this is what we want to prove. Okay, hopefully in an hour. What I want to assess in the first 5 minutes is how much of motivation, how much motivation or background should I give to this? So what do I mean by motivation? First of all, why would you want to prove something like this? And why would you even suspect something like this is true? And then once you get a feel for why the universe suggests an inequality like this is true, we can actually jump into the bread and butter of the proof. So let's take a vote. Those who want some background motivation for why you would want to prove something like this, or why you would suspect an inequality like this is true, raise your hand. Okay, all right. Those who, the inequality is obvious that something like this should hold, we want to jump into the proof right away. Raise your hand. Okay, so it's half-half. So I'm going to do both half. So then we're going to give some examples for why you should suspect an inequality like this is true. As a matter of fact, I'm going to prove a statement that's true over all functions, and then I'm going to restrict to fixed points. Okay, all right. So why would you suspect something like this is true? So first, let's describe what we're talking about. So we want the maximum cardinality of what I call these edge labels. And the edge label is the absolute value of, let me write it this way, minus sigma I in Zn. Okay, so the picture you want to have in mind is that you have some graph. Let me draw the graph, example of the graph. And you want to label the vertices. That's what sigma is doing. Sigma is a permutation on the vertices so as to maximize this cardinality. Now, why would you expect an inequality like this to be true for arbitrary functions? So the example that is most compelling to me is 2 cycles. So you can consider a function like this, which is a union of 2 cycles. And now you can play the game. You want to create as many distinct edge labels as possible. And the way to do that, I mean, you cannot create more than, in this case, 6 divided by 2, because these guys will always have the same edge label no matter what you do. Okay, so let's make a worst possible labeling first, and then ask for help to improve. Okay, so this is the possible worst in terms of cardinality of this set, because everything is 1. Suppose I wanted to make it as large as possible. What relabeling can I do? So sigma is what I apply to all the vertices to come up with a new labeling. So any help from the audience? It's not considered cheating if I ask for help from the audience. Any help for making as many different edge labels as possible?
You could keep them all the same, except sigma 1 is 5 and sigma 5 is 1.
Okay, so all right, so let me check. So you said, so an easy way to do it is what number should I put?
Okay, yeah.
So which number do you want here? 0? Okay. 5.
2 and 3.
2, 3.
And then 4 and 1.
4 and 1. Okay, so if we do this, these edges, this has edge label 5, this has edge label 1, 1, and this has edge label 3 and 3. Okay. So these are 3 distinct edge labels. Okay, so, and that's the best you can do in this case. But if you compose this function with itself, you get the trivial identity function. And for the identity function, you can only get 1. Doesn't matter how you label. Okay, so if you get the identity function, basically you get a fixed point at 0, fixed point at 1, fixed point at 2, fixed point at 3, fixed point at 4, fixed point at 5. And it really doesn't matter how you label it, you always get 1 distinct edge label. So you get 0 everywhere. And you can see here that the number of distinct edge labels that you get here for the maximum is bigger than here after you compose. That's all I saw as evidence. And so therefore I said there has to be a theorem here. But the motivation for why you want to prove this is the graceful labeling conjecture, which I'll say some words about once we get into the proof. Okay, so that's the motivation. One is some motivation, some evidence. I looked at the more graphs, to be honest. I implemented in Sage quite a few functions to check whether this inequality is always true. Now, this inequality is not strict. You need the equal sign, because if you have a graph that is made of odd cycles, composition doesn't change the function. The function, you still have a 3 cycle in this particular case. So therefore, the number of a maximum is not going to change. So the inequality is not always strict. You need the equal sign. Okay, all right. So that's for the statement. Any question on the statement? Any questions? Don't be shy. The video can be deleted. Yeah. So any question, and there are no bad questions. I take the blame if somebody regrets a question. So no questions? We can jump into the proof? All right, so this inequality is what we want to prove. And we'll prove something slightly more general. But we need to set up some helper lemmas that are going to be useful for us. So the tool we're going to use, and this is biased to my training, is polynomials. So we're going to use the polynomial method to prove this inequality. And let's start talking about the tools. All right, so I should keep track of time, right? I hate it when speakers go over time, so I'll try not to go over time. Okay, so tools. Tools are polynomials. So ring of polynomials. And the ring we care about is Q, and there's a variable for every vertex of your graph. So each x corresponds to a vertex variable. Now what we want is to come up with a polynomial that sort of detects for us whether the maximum is n or not. So what we want is we want some p of x depends on x. P of x is 0, xn minus 1. And admits a non-zero value on Zn to the n. So there's an assignment on Zn if and only if the maximum cardinality sigma f sigma inverse of I minus I in Zn is n. I want to detect when a graph has maximum cardinality. So a good example to keep in mind is the path. So the picture to keep in mind is the following. So there's going to be a variable here, let me call that x0. There's going to be a variable x1. There's going to be a variable x2. There's going to be a variable here, x3. And the goal is to come up with some polynomial that describe assignments to these variables such that the maximum is n. And change to the variable is what sigma describes. So for example, if you assign x0 equals 0, and you assign x1 equals 0, 1, 2, 3, 0, 1, 2, 3, 3. Okay, let me ask for help. x2 equals question mark, and x3 equals question mark. How can I make sure that the absolute value are different? So my labeling so far is 0. Here I put 3. Here I'm asking what to put here and what to put here so that the edge labels are distinct. So 0 is free. I didn't have to work for 0. 3 is what I give. Okay, so what can I put here and here to get different edge labels? Any idea? Yes?
1 and 2.
All right, so if I put here 1 and 2, then this guy is going to be 2. This guy is going to be 1. Okay. So that means that if you make the assignment x3 is equal to 2, x2 is equal to 1, x1 equal 3, and x0 equals 0, you get n distinct edge labels. And that's what we want. So the polynomial that we want to construct sort of has to tell us that this can happen. Okay. The polynomial typically is not going to tell us where it's going to happen, but so let's construct the polynomial. That's the first level. So the first tool is this polynomial. So pf depends on the variables up to xn minus 1. And it's the following polynomial. So you do the product over all I less than j. So for all pair ij, where I is less than j, you're going to look at xj minus xi. And this constraint makes sure that you never assign the same value to two. As every time you assign the same value to two different vertex labels, you get 0. Okay, so this makes sure that you never assign the same label to two different vertices. And then you need to implement something similar for the edges. So for the edges, we're going to look at x, f of j minus xj squared. And here is x f of I minus xi squared. And this is the polynomial Pf. Now, the claim is that if there is an assignment to the variables where the cardinality is n, this polynomial takes some definite value. And if there is nowhere, then this polynomial vanishes everywhere on the n to the n. Okay. And we want to get a feel for why that's the case. So claim Pf evaluated at some point, let's say u0, u1, all the way up to un minus 1, okay, is going to be either plus or minus product I less than j of j minus I times j squared minus I squared if the assignment u is graceful and 0 otherwise. All right, so now let me explain. So you plug in some numbers, and the only numbers you're allowed to plug in for the variables, so I should say something about the u's, right? So ui is in Zn. You assign some values, okay? There's no restriction. They just have to be in Zn. And the claim is that either this polynomial comes out to be plus or minus the product of all the difference of integers between Zn times the square between, okay? Or it's 0, okay? For every single point you plug in Zn to the n. Okay. Now why that's true? Why is that true? Well, if you plug in a point such that two vertices are assigned the same vertex label, you get 0. So to get this part to be non-zero, you need distinct integers. But as soon as this is non-zero, you get the product of j minus I, because all the integers are there. Okay. On the other hand, if you make an assignment of distinct vertices, distinct labels to the vertices, and the edge label repeats, then there's going to be a cancellation in this factor. Is it clear so far? Should I unpack this? Forget the camera. The camera has gone. So should I unpack what's happening? Why is this true?
I mean, I don't get why that's true, but
okay.
Motivations, you know.
Well, if they're all distinct, which they have to be, then you're going to end up with each of the values for the differences.
Yeah, so that's a good point. Okay, great. Please, Aaron, do not let me go by. Do not let anything go by.
I figured you were getting to it, you know.
Yes, all right. So every edge, we said every edge is something like xi goes to xf of I. Every edge is something like this for every I. Now, what this is saying is, look at the difference x f of I minus xi. And then square it. Square is an algebraic operation, unlike the absolute value. So the label of this edge is going to be the absolute value square of xf of I minus xi. Okay? Now, I have n edges. Every vertex has exactly one edge leaving the vertex. So I need to check whether all the pairs of edges have distinct edge labels. So this van der Waals product, so this is the product over all the pair. So I'm looking at the pair xi f of I, and I'm going to look at the pair xj going to x f of j. And I want to make sure that these are assigned distinct labels, right? Okay. Now, if you look at the square of numbers between 0 and n minus 1, if they're all distinct, then you're going to have 0 squared, 1 squared, 2 squared, 3 squared. So all the squares should appear. That's why we have the j squared minus I squared. Because all the integers between 0 and n minus 1 have appeared. Yes?
Okay, wait, so to clarify, in the product on the left side, I and j is talking about like the indices of the vertices.
Yes.
But here I and j is just saying if you were to iterate like through all the actual numbers 1 through
Exactly. Okay, great. That's a very good clarification. So let me do this. Let me write UV to emphasize that they're playing a different role. So this is UV, and this is V squared minus U squared. Oh, sorry, this is V minus U first. V minus U, and this is V squared minus U squared. So this VU, these are actually assignments to the vertices.
Yeah.
And this V squared minus U squared, these are actually the result of computing the difference along every edge.
But this is constant depending on n. This doesn't have anything to do with the values you're plugging into this.
So when you have a particular polynomial, what's going to happen is if you plug in the value, you plug in these values in your polynomial, I'm saying the outputs, they're only basically in absolute value 2 possible outputs. Does that make sense? So let me show a concrete, let's do a concrete, very small example to see what I'm talking about. So suppose I'm looking at a trivial graph. Okay, let me call this guy x0, and let me call this guy x1. So if I was computing I'm computing this polynomial. Okay, so what I would look at is, the first one would be x0 minus x1. This makes sure the vertices are assigned distinct edge label. Okay. Then the second factor is going to be, unfortunately, not so interesting, but let's write it. So this is going to be x0 minus x1 squared. And this x0, where did it come from? And if all the edges are distinct, then you get a non-zero. And the only non-zero you can get is plus or minus this quantity, because you did the product of distinct integers, or you did the product of the difference of distinct squares. And you don't have a choice. These are the numbers you get. Does that answer your question?
Well, I guess what I mean is this polynomial only has 2 values that it admits. It's either 0 or this product.
Yes.
And this product is just some function of n, right?
Yeah, absolutely. Yeah,
Okay.
I agree. Actually, to be completely honest, the polynomial can take 3 values. It can take either 0 plus this quantity or minus this quantity, just depending on the orientation.
So like, right now this polynomial, when you plug it in, I guess you get what, -1?
Yes. Yeah.
You're not really going to be able to come up with any other graph on 2 vertices, but let's say we did a graph on 5 vertices.
Sure.
And we got a value of...
Like something like this. Okay. x2. x1. Yeah, okay, right. So you had a graph already on 3 vertices is interesting. So go ahead.
And we get some non-zero value, because we can label it gracefully.
Yes.
And whatever that non-zero value is, let's call it like S.
Sure.
If you then have another graph on 3 vertices,
Yes.
and you give another graceful labeling, it'll be the same value plus
Same number. Yeah, absolutely. The number you get at the end is only keeping track of the product of the differences. So whenever a labeling is graceful, the number you get is the same. Always get the same. In absolute value, the same number. Because all the number does is check that the product of the difference of all the vertices are different. So that's going to be exactly product of V minus U. And it checks also that the edge labels are all different, but the edge labels are between 0 squared up to n minus 1 squared. So you cannot tell from the evaluation of the polynomial which graph was being labeled. The graph information is lost. You can only tell from an assignment that it has a graceful labeling. So the name of the game is to come up with a clever way to find out that there exists a point on the grid Zn to the n where the polynomial does not vanish. Because the naive way to do is to plug all the values and check. And that would take too long. Definitely more than an hour. Any questions? Any other questions so far? So the polynomial we want to look at is this one. This is the one we want to focus on. And it detects for us whether an assignment is graceful or not. So far so good? Okay, all right. So that's the first tool we want to use. That's the polynomial encoding. Now, how do you detect that a polynomial has a non-vanishing point. So this is the next step. Evaluation of a polynomial. So studying evaluations. All right, so this is a trick I wish I was given when I was a graduate student. Okay, so it turns out that evaluation of polynomial and Euclidean division are basically one and the same. Okay, so what do I mean by this? So this is a fact that was pointed out to me, that if you have a polynomial p of x, and you compute the remainder, and I'm going to make sure we're on the same page, of x minus a, okay, that this is going to be congruent to p of a. So this is discrete math. I know this because I'm teaching the class, and Aaron was a TA. So what this says, okay, so what am I saying? So you have to do your favorite Euclidean division algorithm. So you take p of x, and then you put x minus a. Different school systems have a different place where they put the divisor, the quotient. I don't know what is your school system do, but when I was taught, I put the quotient here, x minus a, and I put the dividend, p of x. And the quotient comes here, and the remainder is in the bottom. It doesn't matter where you do it. But what is interesting to me is that if you do the division and get the remainder is going to be p of a. Okay. Those who've seen a proof of this, raise your hand. Those who've never seen this. Okay, so what this means is that for somebody doing algebra, Euclidean division is equivalent to doing search and replace. And I did not appreciate the importance of search and replace until I heard that even biological cells have implemented search and replace. And it's called CRISPR for the biologists. I don't know anything about biology, so let me not get in trouble. Okay, so how do you prove something like this? The idea is to look at the polynomial, let's call it the coefficient alpha k, x to the power k. Okay, so let me call this px. And k goes up to the degree and starts at 0. Every polynomial can be written like this. Okay? There are many proofs of this, but my favorite proof, and we're going to use this over and over, is the telescoping argument. So I'm going to write p of x as x minus a plus a raised to the power k, and then this is still p of x. I just added a 0. I haven't changed anything. But thanks to teaching discrete math, which I recommend to anybody, we know the binomial, what the binomial theorem says about this. And the binomial theorem says that you can rewrite this part as sum over, here is I, choose k, and here you can write x minus a to the I, and here is a to the k minus I. Yes? I goes up to k, starts at 0. But remember, we said that every time you're multiple of x minus a, we take you out, because that's part of the divisor. We want whatever is left when you're not a multiple of x minus a. So that means the only term that we care about is the term that does not contain an x minus a. And the term that doesn't contain an x minus a is going to be a to the k. Right? So that you get rid of all the other terms except for a to the k, and you're left with alpha k times a to the k. And alpha a times a to the k is p of a. Everybody sees? And this intuition is really, really useful. That when you look at modular arithmetics, what you're really doing when you get the remainder is plug and play. You are literally doing a search and replace. Find x and replace by a. That's the most important idea of my life. So, okay, all right, so now let's use this let's use this. It turns out things are even more interesting. Suppose you had many variables. Suppose the polynomial that you're modding by was not degree 1, was degree n. And we're going to pick a very special polynomial because we care about the behavior of our polynomial on Zn, on the Zn lattice. So we really want to know how the polynomial behaves when you plug in either 0, when you plug in 1, up to n minus 1. These are the values I really want to plug into the polynomial. And in some sense, I want to plug them all at once. If I could, I don't want to try them one by one by one. I want to plug them all at once. And the beauty of Euclidean division is that in some way, you can do just that. You can plug all the values at once in your polynomial. And let me write down the claim. And that will prove. All right. So here's the claim that if you take any polynomial, this is worth a new piece of chalk. It's worth a Hagamoto piece of chalk. So if you take any polynomial px and you do Euclidean division modulo x minus 0, x minus 1, all the way up to x minus n minus 1. I don't want to write this all the time. The shorthand for this is falling factorial notation. Okay. Then the claim is that this thing here is always congruent to, let me write, the sum over, let me write I in Zn. And here I'm going to write P of I. This is the plugging in part. And here I'm going to write product of x minus j, I minus j. And here is j different from I, but is between 0 and n minus 1. So these polynomials are very special. They are the so-called Lagrange basis polynomial. They're non-trivial polynomial. If you expand them, they don't vanish. But what it says is that if you care about the behavior of a polynomial at the point 0, 1, and n minus 1, do Euclidean division, your favorite way of doing it, and the remainder is going to be a linear combination of the Lagrange basis where the coefficients are evaluation of your polynomial. So this is as close as you can get to plugging in all the values at once. If you care about how P0, P1 all behave, divide by this, and the remainder is a linear combination of these guys. Okay. Those who've seen this claim before, raise your hand. Those who've never seen this before. All right, so every good talk should have a proof and a joke. So let me at least give a proof. So this legitimate a proof of this. Now the reason I want to prove this carefully is because in a second, I'm going to generalize this to multivariate polynomials. And that's non-standard. So what I'm going to show here, this is standard. Freshman honors discrete math student with a good TA would have seen something like this by the end of the semester. But the multivariate version that we're going to use to actually prove the lemma is not a standard result. Okay, so how do you prove something like this? So what you need is the so-called quotient remainder theorem. Now, what is a quotient remainder theorem? It says P of x can always be written as, let me write Q of x, times the divisor, which I took to be, let me write my notation, x, the n. This stands for this guy, x minus x0, x minus 1, all the way to x minus, plus a remainder. The remainder is r of x. And the quotient remainder theorem says the degree of r of x is strictly less than degree of x n. That if you do division, your remainder has degree smaller than the degree of the divisor. And the degree of the divisor is n here. So the remainder is going to have degree at most n minus 1. And what's interesting about the quotient remainder theorem is that this expression is unique. There are no two ways. Okay. I don't have 2 hours, so I'm not going to prove the quotient remainder theorem, but I can refer the viewer to wonderful YouTube videos proving the quotient remainder theorem. I'm going to assume the quotient remainder theorem, and then I'm going to use it to do this. Okay, so what we're claiming here is a statement about R of x. Now, to see what's happening, we have to ask ourselves what happens if you compute pi. So if I compute pi according to this expression, pi is going to be qi times I n, okay, plus R of I. Now in, you have to bear in mind that this is I minus 0, I minus 1, I minus 1, I minus 2, all the way up to I minus n minus 1. Yes? What is this going to be?
0.
It's going to be 0. So for every I in Zn, for all I in Zn, this part of the polynomial vanishes. 0. So you're only left with R of I. So that means that over Zn, you cannot distinguish P of x and R of x. There's no way to tell them apart. If you're only allowed to plug in points over Zn, there's no way to distinguish P of x and R of x. But, yes?
So is this where the connection to interpolation comes?
Absolutely. Yeah, because if you have a polynomial of degree at most n minus 1, and you're plugging in, you know its evaluation on n plus 1 points, then the polynomial is uniquely determined by Lagrange interpolation. Everybody sees? So here, R of x has degree at minus 1. Okay, so by interpolation, basically, the claim follows. The claim follows. This is standard, so I'm not making a fuss. I don't want to sound clever proving standard things, but I want to sound clever proving non-standard things. And this is standard. If you have a polynomial of degree at most n minus 1, you can actually write down a system of linear equation and you get the coefficients. Polynomial of degree at most n minus 1 is determined by n evaluation points. And if you have the n evaluation points, you can tell the polynomial. So this is R of x. This is explicit expression of R of x. And what's nice about it is that its coefficients in the Lagrange basis are the evaluations. In particular, if the polynomial vanishes over Zn, the remainder will vanish over Zn. Yes? Okay, good. So now, all of this is standard. Let's do some non-standard things. So let me write now the multivariate version of this theorem. So here's a non-standard type multivariate statement. And this was not at all obvious to the experts. I thought this was completely trivial, but I showed this to a few experts and they told me they do not believe this. Because, I mean, you have to be careful. Multivariate polynomials are tricky. They're really, really tricky. And there's something very special that I'm using. And it was not clear to me until a long time after, what was special, why would this thing working? So let me write. So the claim is that if you now are interested in some polynomial in n variables, and the polynomial you should have in your head is this Pf. That's the one we care about. And you care about how it behaves when you evaluate it over the grid. So what does that mean? You have to evaluate every variable xi n, and here I has to be in Z. So you sort of have to basically do Euclidean division with respect to every variable. Now, in general, when you do Euclidean division with respect to every variable, the order in which you do the division matters. In other words, depending on the ordering of the variables you use, you may get completely different answers. But it turns out that in this case, it does not happen. There's only one remainder you get. And I'll tell you at the end why that's the case. So this polynomial is congruent to, okay, so let's write it. So it's congruent to sum over, let me say, u in Zn to the n. And this, you should think interpolation. What I'm going to do is I'm going to plug in all the values and write down some linear combination. Okay, so what am I? So here, this is going to be p u0, u1, all the way up to un minus 1. Okay. So again, it's as if I'm plugging in all the points on the grid. Okay. Now I need to write the analog of the Lagrange interpolation basis. And it turns out you can. So here's what it looks like. It looks like I less than n starts at 0. And here is going to be product of j subscript I is in Zn minus the, okay, I have to remove something. Let me decide what that something is. Oh yeah, okay, it's ui. Ui is the value of over. Okay, and here, this is going to be x subscript I minus ji, and this is ui minus ji. This is the multivariate version of Lagrange, which says, forget about all the variables, interpolate in x0. Then, take the result, forget about all the other variables, interpolate in x1. Then, take the variable x2, interpolate. And if you do that, this is the polynomial you get. Okay. What? Because if you forget all the other variables, what you end up with is the thing we had before. You end up with this product of x minus j divided by I minus j. For each of the variables, if you look at the expression, it looks like this. There's some value you're skipping. J has to be different from I. J has to be different from I. But then you're doing the product over everything. So this is doing Lagrange interpolation for every variable independently. Now, the reason this works is because the places where I'm evaluating the polynomial have simple roots. In other words, I'm not looking at a polynomial like this, xy. If I had a polynomial, okay, xy doesn't feel fair to us. If I had a polynomial like this, x0, x1, this does not have simple roots. There's a continuum set of roots. Right? If you pick x0 equals 0, it doesn't matter what x1 is, you have infinitely many roots. So the division algorithm is not well defined if your polynomial does not have simple root. That's one. Second thing I'm using is that each of the divisors is univariate. And if each of the divisors is univariate, you can safely do Lagrange interpolation in one variable at a time. Okay. All right, so now let's prove this. Let's prove this. There's a proof very similar to this, but there's also a linear algebra proof. So let's take a vote. Which proof do you guys want? There's a linear algebra proof. Wait a minute. We have 7 minutes left. There's a linear algebra proof. There's a proof that looks a lot like this one. We get to choose. Okay, linear algebra. All right. That's a very good choice. Excellent choice. Any other choice would have been unacceptable. So let's do the linear algebra proof. So the linear algebra proof says, so here's linear algebra proof. So the linear algebra proof is going to proceed as follows. It's going to say, I want to treat polynomials as if they were vectors. I want to be able to do inner product of polynomials. I want to say that polynomials are orthogonal, and so on. So I need to define an inner product on polynomials. So here is my inner product. By the way, the whole of this proof, if we come for episode 2, is all linear algebra in the hood. The quotient remainder theorem is a linear algebra statement, because if you expand the polynomial, you write a van der Waals matrix, and you're really inverting a matrix. So all of this is linear algebra in disguise. Okay, so inner product. So you give me P x0 up to xn minus 1, and you give me Q x0 up to xn minus 1, and these are polynomial in the ring that we care about, xn minus 1. So the inner product that I'm going to use basically looks at P u0 up to un minus 1, Q u0 up to un minus 1, and I sum over all u in Zn to the n. Okay? So if you look at this, then polynomials are really vectors. This is a vector of dimension n to the n, because they're n to the n points. You plug in the value of u, that's how you get the entries, and you multiply by the corresponding value of p, that's how you get the entries, and whatever you get, we call this the inner product between the polynomial p and the polynomial p. Okay? Now, why would you do that? It turns out that if you use this inner product, the Lagrange bases form an orthonormal basis. They are pairwise perpendicular. Let's find out why. Okay, so let me write the Lagrange basis. So this is an inner product. Let me describe a basis for a vector space. Okay, so here we go. So I say, well, I look at the following basis. I'm going to look at polynomials of the form i's, and here product ji. My God, I'm becoming like the. I don't want to go over time. That's a religious no-no. Okay, so Zn minus ui. Okay, I'm just rewriting this polynomial, which is xi minus j subscript I, and here is ui minus ji. Okay. And of course, there's a polynomial like this for every vector u in Zn to the Zn to the n. So this is a set of n to the n different polynomials. For every u you take, every n values of u, I can construct a polynomial like this by plugging your values in the denominator. Okay. So this has n to the n distinct polynomials. All right? Okay, so now let me compute my inner product. All right, to compute the inner product, I need to multiply two polynomials like this. So I want to avoid confusion. So let me call this Li. Let me call this vector F. Okay, all right. So here's a polynomial. Let me call this guy Vi. And I'm going to multiply by another polynomial of the same kind. So this is I. This is product of ji in Zn minus ui. And here is xi minus ji divided by ui minus ji. Okay, and now I need to evaluate this polynomial. I mean, right now there's no sum. I just multiply these two polynomials. Yes? I'm trying to set this up. I'm trying to have one to be q and the other to be p. Okay, now, once you have this, you have to sum over, let me call it w and Zn to the n. And you need to replace each one of these guys by wi. And here, I'm going to put wi. Now, I told you that this is a Lagrange basis. The way the Lagrange basis works is that it's 0 everywhere except one point. In every variable, that's what it does. So the Lagrange basis at 0 is 0 everywhere and is 1 exactly at 0. The Lagrange basis L1 is 0 everywhere and is 1 exactly at 1. So what's happening here is that if these Lagrange bases, if this ui and this vi are not aligned, whenever one is 1, the other is 0. And whenever the other is 1, the other is 0. So this comes out to be, this inner product comes out to be 1 if the vector u is equal to the vector v, and 0 otherwise. It tells us that with respect to our inner product, the Lagrange bases, these n to the n vectors, are orthogonal. Not only are they linearly independent, it's an orthonormal basis, the best basis in the universe. Once you have orthonormality, you're done. Because if you have an orthonormal basis and you want to express a vector, all you need is to project. So how do you write down a vector in your basis? So you pick your favorite polynomial, p of x. And if you want to write it, all you do is you pick your u in Zn to the n, and then you do your inner product. So you take your p inner product with your Lagrange basis, let me just call it Lx, in u, this is x vector times Lx. Each Lx is something like this. This is what I'm calling the Lx. And now we define the inner product. We know exactly what the inner product is. It's the evaluating of Lx at p. I mean, evaluation, right? You do the sum over the evaluation. It was 0 out everywhere except at u. So this comes out to be p of u0. This algebra and linear algebra proof. We're done. We said that every polynomial admits an expansion like this. And basically, this is unique because the quotient remainder theorem tells us that if you have a polynomial of degree at most n minus 1, in each variable is the unique quotient. So there's no two polynomials that have this behavior. All right. We're out of time. But suppose you wanted to continue the proof. What would you do? Basically, in one word, you would take PF and you would compute this. But right now, it's not realistic. Right? This is evaluation over n to the n points. So this is not a viable strategy. You need to be a bit more clever than this. But what I did want to convey in this first session is that you can basically extend the Euclidean division to multivariate polynomial as long as your divisors are univariate and have simple roots. And that's what we want to do to PF. All right, yes?
So where exactly do we rely on the fact that the roots are simple? And
so in our division, okay. So when I explain how you compute your remainder, I told you can evaluate your polynomial at these endpoints and look at the evaluation value, right? I said R of x and P of x are not distinguishable. But suppose you had a polynomial like this, x minus 0 times x minus 1. You just lost an evaluation points. Right? The remainder is still going to be a polynomial of degree at most 2. If this was my divisor, the remainder after division has to be a polynomial of degree at most 2. But it's no longer the case that I have 3 points to evaluate the polynomial at.
So you lose your basis.
I lose my basis, exactly. So equation division doesn't really care about this, but the Lagrange interpolation interpretation no longer works here. So I could not write a formula like this down, like I did before. But if the roots are distinct, then I can really think about the remainder as interpolating over them. So
this really is more lineage than
polynomials, yeah. I mean, if you ask me, all of polynomials is really linear. But opinions differ on the topic. But yes, it's basically lineage under the hood. Okay, yes?
Where does this tie back to the
Yeah.
the PF as in
Yes,
like
very good. So that's a very good question. That's a good way of wrapping up everything we've done so far, right? How does that connect to what we are doing? Okay, so let's point this out. So what we want as a wrap-up of everything we said today is the following statement that we basically proved. So here's the claim. The graph of a function f, okay, of where f is a function from Zn to Zn, okay, admits a graceful labeling if and only if Pf modulo, here is where I do my division thing, xi to the n I in Zn, this is not congruent to 0.
because it's adding up all.
Yes, all the evaluation points.
Can it be possible, because the evaluation points could be plus or minus?
Absolutely, yes. But thanks to the Lagrange basis,
Oh.
these are linearly independent. They don't collide. The Lagrange basis keeps them all separate, so they don't mingle. So this is where we're going to use this. I mean, what's frustrating at this point is that this is not efficient, right? You don't want to have to evaluate n to the n point. That's even worse than trying all permutations. But that's the intuition. We have to somehow say that there is a point in the grid, depending on properties of f, not of the polynomial business, which guarantees a non-zero evaluation point. That's the idea. But this is what we want. So the statement is, we've converted a problem of graphs and functions into a statement about polynomials. So if the remainder of this polynomial does not vanish, and you can get the remainder either by doing Euclidean division or by doing Lagrange interpolation. It doesn't matter how you get it. If you get the remainder and it's not the identically zero polynomial, then you know somewhere there is a labeling. And what is the bad news about this method is that it will not tell you where it is. You will get some remainder, and it says somewhere there is a labeling, but I cannot tell you where it is. That's not an artifact of me. Polynomial method typically does not supply efficient algorithms. It supplies existent results. And that's as far as we will go. Okay, all right. Thank you thank you to the organizers. We'll see if there's a part 2 to come.
Well, but what you just said, that gives rise to the joke that you...
Yeah, right. Right. So the joke is that we did not do the whole proof.
Yeah, no, it's not, I didn't do that. Sorry, I meant there's a joke of there's like a mathematician, an engineer, and a physicist in a building, and it's burning down, and the physicist crafts some way to, does a calculation, finds a way out. The engineer ties some bed sheets together, and it gets out of the mathematician, writes, thinks a bit, writes something down, discovers there exists a way to get out of the building, and then,
And stops there, right? Sure. He's reduced to a problem we know how to solve. Yeah, that's a nice joke. Thanks. All right, thank you.